Okay, hi everybody. Let's get started with the acid and bases lecture for fall 2016. Okay, so really quickly, what is an acid and a base? I'm sure you remember from general chemistry, but just to refresh your memory, acids and bases can be qualitatively differentiated. So acids are sour and corrosive, like, for example, citric acid, which is responsible for the sour taste in lemons. And bases are bitter and slippery, and remember that they neutralize acids. Some examples of bases are alkaloids, like caffeine and morphine. Also nicotine is one. So here are some examples. There's acetic acid, and here is caffeine and alkaloid. So perfect. So this guy is a base, this guy's an acid. So we're going to define acids and bases in three different ways. The first one is Arrhenius. And an Arrhenius acid or base, it's a very simple way of thinking about it. So Arrhenius, it's going to be an acid which, when you add it to water, it increases the concentration of H plus ions present, and a base is going to increase the OH minus ions present. So, for example, we have HCl and NaOH, and when they're added to water, they dissociate, and you're left with H plus and Cl minus, which increases the H plus concentration. And when you add water to the NaOH, you get this Na plus and OH minus ions, and it increases the amount of OH minus. So very simple. So here is an example. It does not say explicitly H2O, but just imagine that we're putting H2O in with the HCl, and it's separated into, like I said, the H plus and the Cl minus. Same down here. So that would mean then that acids defined by Arrhenius are always going to be acids that that increase this concentration of this H plus. So they have to have this hydrogen here. Likewise for bases, so the definition is really narrow, right? So you can only have a base which donates the OH minus. So a base has to have OH minus. So that's why Arrhenius is a very narrow description of acids and bases. So let's keep going here. Here are some problems. Go ahead and try it by yourself. Take a moment. Okay, so after you've tried it, let's go ahead and go over it. We're classifying these compounds as either an acid or a base using Arrhenius. So pretty simple, right? So this first one, like I said before, Arrhenius acid, it has to, So Arrhenius acid, it has to have this hydrogen here, and which it does, and when it separates, it'll separate into NO3 minus and H plus. So that's going to increase the amount of H plus, so it's an acid. There we go. This one, you see it has the OH here, so it'll separate into the K plus and the OH minus. So it is a base, and it increases the OH minus when it's added to water. So same thing here. This will separate into Ca 2 plus, and then we'll have these separate as well. So we'll have 2 OH minuses. And so that's a base, because again, we're going to get more OH minus, not more H plus. And then here again, we have that hydrogen sitting there. Even though it has the 2, don't worry about it. It will, it's still going to break apart into H plus and SO4. So, good. All right, Bronsted-Lowry. So Bronsted-Lowry is going to take it into a different kind of definition of acids and bases. So an acid is now a compound which is donating a proton, and a base is a compound which accepts a proton. So, and most importantly, with Bronsted-Lowry, it expands Arrhenius a little bit because now bases don't have to just be something with an OH. They can be something that accepts a proton. So what do we mean by that? Well, we have this example here. So you have the reactants on the left-hand side, the products on the right-hand side. So let's go from left to right in this reaction. Remember, you can go right to left as well, but we'll focus on left to right. And you have to take your two reactants and look at the products and tell yourself what happened to each reactant. So the NH3, if we looked at the product side, it has become NH4, so that means that it's picked up a proton. So if it's picked up a proton, does that mean it's donated a proton or accepted a proton? Well, it means it's accepted a proton. And we know it's picked up this proton because it has this positive charge here. Remember that protons will add a positive charge. And it also literally has one more hydrogen. Then let's look at H2O just to further convince ourselves that we know what's going on. So H2O, we look over here, oh, it's lost a hydrogen. It's picked up a negative charge, which we would expect if something loses a proton. So that means then that, so if H2O has lost a proton, is it donating or accepting a proton? Well, it's donating. So that means H2O donated a proton. It is the acid going from left to right. NH3, it has picked up a proton, so it is the base. Pretty simple. It just makes bases more universal than just bases with hydroxide. So here we have a little example. So this top part here, this is the really simplistic example of Arrhenius. So we have HCl, we throw in water, and you get this H plus and the Cl minus ions. So we know it's an acid because over here we have an increase of H plus ions. Okay, so that's Arrhenius. So now look down here. It's the same reaction. So now we have HCl plus H2O, and you get H3O plus and Cl minus. So now we want to talk about Bronsted-Lowry. So we look at each of the reactants. Notice we're going from left to right explicitly here. So HCl, what happens to that? Look over here. Oh, it's lost a proton. So it has donated its proton because it's lost it. And this H2O, what's happened with it? Well, it's gained a proton. So then the proton donator is the acid, and the proton acceptor is the base. Remember that you can use your Lewis dot structures to help you figure out where the electrons are. And remember, there's electrons here between this chlorine and this hydrogen. So let's add them to everybody here. So this is important because these species will use their electron pairs to pick up protons. And when they donate a proton, they will take the electrons in the bond and take them back onto them. So for example, there are electrons here in this bond between H and Cl, and the chlorine ends up taking those electrons that it was using to bond, so it was sharing with the hydrogen, back onto itself. So that's important because also you can see that this oxygen uses this pair right here to bond with the hydrogen that the HCl contributes to it. See, it does not have that pair here. So it's good to brush up on that. But just to be clear, water uses the lone pair to pick up the proton. So it uses one of these lone pairs to pick up the proton. And we'll show that with an arrow here. And you're going to see a lot of arrow notation with acids and bases and all the way through your organic chemistry education. So it's a good thing to start to think about and get used to. And what we're showing with the arrow is that these electrons are coming over to pick up the proton. So let's go this way from right to left. So if we go from right to left, what's happening? Well, the electrons on the chlorine are picking up a proton from H3O+. And we can see that because if we're moving right to left, what happens to the Cl-? Well, it becomes HCl. So we're just showing that here. Going back to moving left to right though, the HCl is the one that's donating the proton, right? Because it goes from HCl to Cl-, so it's the acid, and the water is accepting a proton. So it's going from H2O to H3O+, and that means it's the base. So here's some problems, so go ahead and try them on your own, and then we'll do them together. All right, so in this reaction, notice that we're only worried about going from left to right. H2SO4, well, what does it become on the other side of the reaction? It becomes HSO4-. That would mean, since it has that negative charge here, but it's neutral here, it went down in charge. That means it lost a proton. And yes, sure enough, it's H2 over here and H there. So did it gain or lose a proton? Well, it lost one. What does that make it? So remember that that makes it the acid. And we have that here. NH3, what happens in NH3? Well, it's neutral here. On the other side, it has a positive charge. So that means that it picked up a proton. And we know that whose proton it picked up? It picked up H2SO4's proton. So it gained a proton. Does that make it an acid or a base? It makes it a base. Here's another one. So go ahead and try it on your own. All right, so did this first species here gain or lose a proton? Well, it's neutral here and it's negatively charged here. That would mean that it's lost a proton, and we see, yes, definitely has. So does that make it the acid or the base? It does make it the acid, right? Donating a proton makes you an acid. Accepting a proton makes you a base. H2O has accepted a proton because it's neutral here, but it's positively charged here. So it's gained a proton, and that makes it a base. A couple more here. So go ahead and try this by yourself. All right, so what's happening here? Well, this goes from being a negatively charged species to a neutral. And so does that mean it gained or lost a proton? Well, it means it gained a proton. And does that make it an acid or a base? It makes it a base. HCl is neutral here, and then it's negatively charged here, so it lost its proton. Does that make it an acid or a base? Well, if it's lost its proton, that means it's donating it. So it is an acid.